everyone, my name is Giulia Laghi and I am a PhD student of the Research Group for Industrial Applications of Plasma of the University of Bologna in Italy. This video is funded by the European Cost Action Plasma Application for Smart and Sustainable Agriculture. To create this video, contributions from various members of the COST community have been collected. This video provides an overview of the most used approaches for electrical characterization in the COST community, along with tips and recommendations for a successful electrical characterization. I hope you will enjoy!
Hello everybody, my name is Richard Zimmerman. I am from Comenius University in Bratislava, and today I would like to show you how to measure the power of dielectric barrier discharges, which are sources, very well known sources of non-thermal plasma, and they can be used for many applications, including gas conversions as well as plasma agriculture. So now I would like to show you the experimental setup. So we have a very common packet-based dielectric barrier discharges just for this illustration. And what is the most important is the high voltage probe, which is situated here, and it's directly connected to the high voltage electrode in the reactor. The another electrode, which is the aluminum foil wrapped around the reactor, serves as a ground electrode. And another very important thing is the capacitor, as you can see here. The capacitor is placed just behind on the reactor on the ground side, and here is another voltage probe, very common voltage probe, which measures a voltage drop across this capacitor. And taking into account the signal from high voltage probe and this probe, we can very easily calculate the discharge power. So now I run the discharge. So here on the oscilloscope, we can see the waveforms of applied voltage. Applied voltage is the yellow curve, and the blue curve is the voltage measured on the capacitor. And now when we draw the dependence between applied voltage and voltage measured on capacitor, we can get this very specific curve, which is called Lissajous figure curve, and it can be inferred very easily that the area enclosed by these curves is related to discharge power. And when we numerically calculate this area multiplied by capacity of capacitor and frequency of the applied voltage, then we can get the discharge power of dielectric barrier discharge.
This video will describe the methodology developed by our group to measure the energy absorption per molecule in the dielectric barrier discharge at atmospheric pressure, audio frequency, and glow discharge plasma. Our large area pilot scale reactor serves as an example. The reactor can be represented schematically as follows. A large area capacitor is supplied by two dielectric layers with a 2 mm gap. The sinusoidal high voltage is supplied by a cascade of a signal generator, audio amplifier, and high voltage transformer is measured using a high voltage probe, while a second probe is used to measure the current across a 50 ohm resistor. To accurately determine the plasma energy, an equivalent circuit model is used, represented here into three parts: the corresponding nonlinear impedance of the plasma, the capacitance of the gap in dielectric layers, and finally, the parasitic impedance. To characterize the later, impedance spectroscopy is performed by applying a high voltage in air without inducing a discharge. A Bode diagram is thus obtained, and the closest fit is used to quantify unknown parasitic circuit elements after subtracting known values of dielectric and gap capacitances. It is now possible to measure the energy of the plasma using this formula, by integrating the discharge current times the gap voltage over a complete period. This methodology was developed to better understand plasma polymerization processes from the small concentrations of monomer flow. Plotting the energy of pure argon and that of the mixture, a constant gap is observed at higher voltage. This energy difference can then be converted into energy per molecule by dividing it by the total number of reagent molecules in the gas flow. Studying this parameter as a function of flow allows to identify the maximum energy supporting two regimes. The model is further validated upon comparing between energy dissipation and bond structure. We are confident that this energy analysis can find application in the agricultural domain.
Hello, I'm Gabriele Neretti from the University of Bologna, Italy. This is our experimental setup and we will show the electrical characterization of a surface DBD actuator that can be used for indirect treatments of seeds, plants or packaging. The reactor is water-cooled to guarantee the reproducibility of the discharge during the treatment. This discharge is fed by a multi-level power supply built in our lab. This generator can produce arbitrary voltage waveforms, and in particular, we will use a square one. To electrically characterize the discharge, you need to measure high voltage, current, and transfer charge. In this way, you can calculate the average power feeding the discharge, and in this way, you can evaluate the energy consumption. The reactor is supplied by a 4 kilovolt square voltage waveform at 16 kilohertz. For this reason, you need a proper measurement setup with proper bandwidth. To measure the high voltage, we use an high voltage 75 MHz probe that is connected between the high voltage terminal and ground terminal. For the current, we use a 100 MHz whole current probe, and the transfer charge is measured by using a 100 nanofarad measurement capacitor and a low voltage probe. For a reliable measurement, you need probe calibration. For active probes like this procedure is automatic by pushing this button. For passive probes, you need to do calibration manually. You can use the oscilloscope 1 kHz waveform in this way, by connecting the probe here and by adjusting the screw for the calibration in this way. And as you can see, calibration is completed. Now we turn on the discharge, as you can see here, and from the scope, now we can see the applied voltage and the current. If I do a zoom in, we can see the current here with 200 nanoseconds per division. Now we can see the transfer charge as a function of the applied voltage. So this is a Lissajous figure. As you can see, this figure is not that clear, and so it is not that useful for the power evaluation. And so for the power evaluation, in my opinion, with this kind of waveform that is not a sinusoidal one, it is better to use applied voltage and the current and not the transfer charge with the Lissajous figure. So as a final consideration, pay attention to the bandwidth of your system and to the calibration of your system. Thank you for watching.
Hello everyone, my name is Olivera Ivanovic. I'm a PhD student of Institute of Physics, University of Belgrade, Serbia. And this is a plasma pin jet that we use in several applications in the plasma agriculture field, such as the production of plasma-activated water for seed germination and wastewater treatment. This is a simple configuration of plasma jet. It consists of a metal body, glass tube, and a central power electrode. For electrical characterization, we use this experimental setup with 3 probes. The plasma jet is supplied by a continuous sine high voltage signal from RF power generator. The current probe and high voltage probe measure the signal at the source, and a voltage probe measures signal across the measurement element in the ground line. The main outputs of electrical characterization are the power dissipated in the system and the power consumed by the discharge. To estimate that powers, we use 2 standard methods. In the first methods, the power is calculated directly from the product of measured time-varying current and voltage. Another method is based on a charge voltage plot or Lissajous figure. By measuring the voltage across a capacitor connected in a series with the grounded sample, the charge flow through the capacitor can be obtained. In the Lissajous figure, the area enclosed by the curve is equal to the energy dissipated per one period of applied voltage. Thank you for watching.
Miniature atmospheric pressure plasma jet, such as the COSJET or the KINPEN, have been widely used in the context of plasma-liquid interaction studies. In this video, I will briefly describe a method to measure the plasma power dissipation of small plasma jet powered with RF signals. This method provides power measurements with good accuracy and uses standard laboratory equipment. For a sinusoidal excitation voltage and a current response that is also sinusoidal, the average dissipated power is given by this equation. An error analysis of the equation shows that very high error is expected for a phase angle close to plus or minus 90 degrees. For miniature plasma sources, this can become problematic because their very small capacitance leads to a highly capacitive load. To avoid such an error, an inductance can be simply added in series with the plasma source. Let's model our plasma source electrically as the combination in series of a resistor and a capacitor when a plasma discharge is present, and as a capacitor only when there is no plasma discharge. A smart choice of the value of the inductance will bring the phase angle between voltage and current close to 0 degree. However, as every real-world inductance has a resistive part, it will dissipate power. To uncouple the power dissipated in the inductance to the power dissipated in the plasma discharge, the power measurement is done in 2 steps. First, the power is measured without the plasma discharge with different current values. From there, the power dissipated by the plasma discharge can be found by the subtraction of the power dissipated in the inductance to the power dissipated in both the plasma discharge and the inductance. Here is the setup we use to measure the plasma power dissipation of a homemade CosJet-like plasma source. Thank you for watching our video.
We will see how transient spark electrospray generate plasma activated water. This is our schemat, where we can see the device we use to prepare the plasma activated water. The water is stored in a syringe and pushed in flow rate of 0.5 ml per minute. The positive electrode is connected to the first channel of the oscilloscope and record with a high voltage probe. The current is connected to 1 ohm resistance to the third channel oscilloscope. A high voltage cable of 10 picofarad is connected to the 10 megaohm ballast resistor to the homemade generator. When the discharge is running, we can see in the first second a corona regime, followed by the first spark. We're running the discharge at 1 kHz. The electric field creates an electrospray which increases the surface of the water for the same volume, facilitating the Ross penetration. Once measured, the data are transferred in an Excel file. We can use them to plot the electrical characterization of our transient spark electrospray. This data could be used to calculate also the mean energy per pulse using the integration over the time of the voltage by the current, and the mean power using the product of the frequency of the discharge by the integral over the time of the voltage and current. It gives us an electrical characterization of our setup with a mean energy per pulse of 2 mJ and a mean power of 2 watts.